So good afternoon to everybody, and I welcome you to the 18th RISIS Research Seminar, which will be devoted to the topics of changing demographics of the global academic workforce. So that's an important topic for research policy and higher education studies. And we have a distinguished speaker, Professor Marek Kwiek, who is UNESCO Chair in Institutional Research and Higher Education Policy at the University of Poznan, and who is an expert and worked extensively on academic workforce data. And we have an equally distinguished discussant from Canada, Professor Samin Aref, who is Assistant Professor at the Department of Mechanical and Industrial Engineering at the University of Toronto, and previously was at the Max Planck Institute for Demographic Research. And he's a specialist on collecting demographic data on academic workforce. So he's really fits the research infrastructure aim of RISIS to take care also of the data part of the analysis of academic workforce. With this said, I remind you the rules Marek will present. Then we will have discussant. The discussant will get the word to make his comments, and then we will have an open discussion. Please mute your micro when you are not talking. You can intervene whenever you want. You are just asked first to open your camera when you want to talk, and maybe if you can to keep the camera open, it's more nicer for the presenter to see some faces than to see just a long list of names. You can intervene by raising your hands in Zoom, by posting in the chat, or simply by opening your micro in the discussion. With these rules of mind, I give the word to Marek for your presentation.
Yes, let me share the screen right now. Yes, I hope you can see it. Good afternoon, everyone. It's a great pleasure to be here. I'm very grateful for the invitation. Thanks so much. I'll be talking about. I hope you can see and you can hear me. I'll be talking about the global academic workforce on the basis of basically OECD data. I'll be studying the past 3 decades, focusing on demographics, especially aging and sex differences, but also expansion in terms of numbers. The structure of the speech. Well, perhaps the most important sentence is here that the global academic workforce is leaving digital traces in their publications. And you can see my approach immediately. Publications, so scientists viewed through publications. I'm moving from publications to scientists, or so to speak, from bibliometric approaches to more global academic profession approaches. I'm using structured big data, structured commercial big data. In this case, Scopus. My approach is in this presentation is largely exploratory. I'm saying why age matters in science studies in a couple of slides. I'm discussing procedures, the data, limitations, and some choices I had to make. I had to make in the process, and I'm discussing the results, basically showing the 3 decades versus a snapshot of the 2020. I'm looking at disciplines mostly and gender, not so much at countries. I'm discussing male to female ratio, and finally I'm zooming in on young scientists and on old scientists to show you the changing demographics in more detail. Well, academic workforce leaving digital traces. We leave traces in our publications. We can combine bibliometric data with biographical data, with administrative data, and all other types of data using record linkage. And this is perhaps the most important word, record linkage. The academic workforce can be traced in different manners, through topics, through time, through cities and countries, through networks, etc., etc. We trace academics in a number of ways. We can trace them as men and as women, as juniors or as seniors. We can trace them longitudinally, which I'm doing today, over time, like 30 years. And we can trace them in points in time. In my case, 2020, just one single year. What I want to draw your attention to is the level of detail and scale available. It's remarkable. We can measure the academic workforce with ever more precision, and it's just unbelievable. I'm using structured big data, Scopus, raw data. I have Web of Science core collection, raw data at my disposal, but for me, Scopus somehow works better. I'm also using National Registry, in this case, Poland, but we can also use National CRIS systems data from a couple of countries in Europe, etc., etc. What is incredible is that we have so huge amounts of data that we can actually discover patterns in how science operates that would otherwise, these patterns would otherwise be imperceptible. And I will show you a couple of examples today. I'm moving from publications to individual scientists as a unit of analysis, from journals and books and publications to, well, in this case, female, but generally to individual scientists. So from millions of publications to millions of hundreds of thousands of scientists and their attributes. This is especially important, their attributes. So the individual scientist is the unit of analysis. Certainly, I'm discussing today demographics, mostly age and gender over time, but we can discuss using structured big data a lot of things, and we know it all at the individual level. And at the scientist individual level, we can discuss productivity and publication types and journals. We can discuss collaboration and its different types, like international, but also same-sex or mixed-sex, which I spent a lot of time on. We can discuss citations as the influence on the global academic community. We can explore, as Samin did, academic mobility, not only national and international, but also, well, cross-sectoral, say academia, industry. The same goes for research funding. The same goes for authorship patterns. Basically, we can study a lot of different dimensions by gender, by age, and finally, statically, 1 year, or dynamically over a period of time. So, well, my focus in this research, changing profile of the global scientific workforce, is the case of 38 OECD countries. Well, we know the focus in research for many years has been graying of the academic profession or aging of the professoriate. We know these terms, but here I'm studying scientists from all sectors. I could be focusing on academia only, but I did it for all sectors. Well, just one word more general. It's probably the first research focus on changes over time, 3 decades, across all 26 disciplines, age groups, and gender. And my focus it's important, is global. It's not comparative cross-national, although I'll be referring to countries, but it's mostly, my focus is mostly global. My final sample is 5 million scientists, and I will show you in a moment how we arrived at this sample. Well, it's exploratory approach. So there's no paper ready, it's paper in progress. And there's popular assumption, untested so far, I would say globally, that the academic profession is getting older. It tends to be understood as there are ever larger cohorts of older scientists. And I'm trying to verify this, I would say, untested assumption. We don't know whether it's universally justified, whether it's correct across all countries or all disciplines, and how it looks in time. So I explore the what, the where, and the how. The what is what can be known about the demographics of the workforce globally, what we can know. The where the potential data can be located, and the how to measure adequately, well, demographic changes at the global level. One more introductory point is careers in science are long. And to the question about a major obstacle in global studies, my answer is, in terms of demographics, my answer is it is access to reliable data pertaining to scientists' age. We don't have the data. So we use academic age as a proxy of biological age, which is a pretty popular approach. Still, there are no more than 20 papers in total using academic age today. Our sample, we have all scientists who appeared at least 3 times in publications in 3 different years in the past 3 decades, including at least once in the past decade. I'll discuss it in a moment in more detail. Now, age matters. I wanted to draw your attention to age. We are used to using age in connection with, well, I would say productivity, most of all, productivity, but not so much age in itself. And age matters. So biological age in itself has been an important social demographic factor in both sociological and bibliometric studies of academic careers for more than half a century. A long time. There were many hypotheses, usually linking aging to performers or age to productivity. I wanted to raise your attention, draw your attention to cohorts. Cohorts come through time and they are at the same age if you look at the Lexis diagram on the right, and cohorts may be more productive or they may be less productive from the moment they enter the academic profession. If you accept people who are scientists who are low productive, they may be so low productive for a long time. So generally cohort matters. Cohort matters. Just a couple of examples of country from the country level. Norway, Canada, Spain, and Italy. Again, it's a connection between productivity and age. We know it matters. Just an example, productivity increases with age, reaching a peak late in careers and declining thereafter. A lot of work has been done in the past 2 decades in which age was linked, biological age basically was linked to productivity. So we know how productivity changes generally in relation to age. Academic age as a proxy of biological age thus far. I'm using academic age, and it has not been used well too extensively. It is a biological age, academic age is the date of the first publication, and it was applied no more than 20 times so far. You have some references here, but generally, I would say it's a good proxy for biological age. We, with my postdoc, Dr. Wojciech Rożka, did a nice study of the whole Polish higher education sector, more than 20,000 scientists, and we were comparing academic age with biological age, which we had, and the correlation is pretty high. The paper was just published in Scientometrics maybe a month ago or so. But still, biological age can be studied through 2 proxies. I'm using just one, date of the first publication, but also date of receiving a PhD can be used. But the data about PhDs globally are absolutely unavailable. In some cases, as in the US, they are available, but it's, I would say, very rare to have large-scale data about receiving a PhD, another proxy. So I'm using the date of the first publication. There are some limitations and biases, and always, perhaps the biggest one is the data set bias. I'm using Scopus. I could be using Web of Science, and they have their own linguistic, geographical, and disciplinary biases. We know it all. We've discussed it for years, like language, English, geography, Anglo-Saxon countries, disciplinary biases, say mostly STEM, etc., etc. However, and that's important, however, other data sets than global bibliometric sources cannot, in my view, cannot be easily used in global studies. They can be used in cross-national studies, but not so much in global studies. So in studies which go beyond single institutions or beyond single countries. And there are certainly other biases like age bias or perhaps most importantly, the last point, we study here only publishing scientists because there's no data about non-publishing scientists at the global level. So it is certainly a bias. I'm studying publishing scientists. I call them active scientists or active researchers in this research. Well, general approach. I'm looking at the current median age, like year 2020, the last year for which the full data are available. I'm looking at the shift in the median age over time in this period of 3 decades across disciplines. And finally, the median age is not everything. I'm also looking at number of scientists. That's why in the title you had expansion of the global academic workforce. So I'm looking at the number of scientists and their age distribution across disciplines. Some disciplines are getting older, others are getting less so older, but still I'm looking at 1 year and at the 3 decades. Data and procedures. Most importantly, globally, the data on academic academic age are not available. At the European Union level, there are some data available from Eurostat, but these are not the macro data, so they're very difficult to be used. I'm using ICSR Lab, which is run by Elsevier, International Center for the Study of Research. And we are getting enormous help from Christy James, data analyst from this lab. So basically, we use the same data which power Elsevier's Scopus, and we use their computational platform. So all calculations are done externally in the lab. Łukasz Szymula, my doctoral student, is doing enormous work here. And this is ongoing work which we are doing together. So major steps in referring to the data. Publications, then first publication, then gender. Well, we're talking about 5 million scientists. Then calculation of the age, well, academic age. Then determining the discipline the scientist belongs to. Then filtering to years, filtering to countries. And finally, we go down and down and down to about 5 million scientists. Well, we had to make some choices in the meantime. We have only researchers who have single country affiliation or single disciplinary affiliation and clear gender and clear academic age defined. We started our research basically with a large sample of 35 million scientists, and we are choosing just 1 year of scientific activity, but it doesn't work. We focused finally on 3 years as a minimum period in those 30 years. So our sample is smaller, but we have those people who are stably present in science, not, I would say, episodic scientists. Well, which measure we have chosen? The median age. It works good for us. There's one disadvantage, well, about the age distribution, but to supplement the median age, we are using age pyramids. So with pyramids especially used to see the distribution of the youngest and the oldest cohorts. Well, now very briefly, the results. That's a very general picture. The median age of the scientific workforce by discipline in the three decades studied. You can see, well, surprisingly, it was surprising to us. The median age is increasing across the board. There are no exceptions at all. The workforce is getting older, the scientific workforce. We looked at disciplines, and we look not only at changing median age in terms of the distance covered by this median age, but also in terms of starting point and point of arrival, not departure here, but arrival. So you can see red points for every discipline, say business. So the median age in 1990 for all scientists in business and economics was 5 years. And today it's 12 years. So you can see the increase in the median age of 8 years. So certainly some disciplines increase their median age much more than others. Also, some disciplines had already older scientists, let's say mathematics or physics, already in 1990 had younger scientists, so to speak, while using the median age as a proxy. And you can see here the changes over time. The median age in 1990 and the median age in 2020, 3 decades later, and the difference. So you can immediately see that the speed of aging differs by discipline. Say it's largest in business and economics, and in the largest discipline, which is medical sciences, med, is relatively smaller. So you see the median age increases in between 3 years in this 30 years and say 8 years. So the differences are highly differentiated. Well, we studied the trend in detail. We used linear trend in this form, which is shown here, where A is a directional coefficient, and we studied the directional coefficient by discipline. So we can see that in all disciplines, the median age increases from year to year. So we can summarize it as all disciplines are aging, and we saw it also in the figure. However, the speed of aging varies, and you can see here on the left this coefficient A, and it's different values. So some disciplines are slowly aging and others are fast aging, but still all of them are aging. We also did regression models. We're thinking about predictions for the future, but it basically doesn't work. There is a significant increasing trend in all disciplines. The average R squared is 0.61, so it's not too much. Still, aging is systematic in all areas. It is, well, it's not a revolution, but I call it here an evolution in science. We are all older, and the aging process is slow but inexorable. Now, let's have a look at in form of a snapshot, just 1 year at disciplines. And it was absolutely fantastic to realize that 40% of the whole global scientific workforce is engaged in medical research. In this single year, in the OECD area, we can study it year by year, certainly, and we did it, but you can see the difference. Medical sciences on the right here, and then just six disciplines in which there are quite a few people, but not too many. And then just compare those humanities or business or economics and econometrics with the number of publishing scholars in the range of 30 to 40,000. There's enormous variation in the number of scientists, and we know where science today global is located, where publishing scientists are located, what is their distribution. And I must say it's enormously interesting to see medical sciences on top of everything, and then biochemistry, then physics and engineering, and all other disciplines, really with a relatively small number of scientists and scholars. To give you an example, all other non-STEM disciplines are small in size, in the range of 30 to 50,000 scholars. The only exception is sociology. Sociology is 130,000. So it's a pretty active and pretty big academic community globally. Now, if we look for a moment at countries, you see where the action is. The action is in the United States. And I'm not talking about publication numbers. I'm talking only about individual scientists. There's absolute domination of the US research globally today. There are only 7 other major contributing countries in the global academic enterprise, and you see the countries on the right, and there's a group of countries with low numbers, and 23 countries out of 38 out of 38, which had no more than 30,000 publishing scientists. So you see how science is globally divided, not by publications, because we know it. We enter Scopus or Web of Science and we know it immediately, but in terms of active scientists in a single year. Now, men and women, I would say especially important. I introduced what I termed male to female ratio, MFR. So I divided the number of male scientists by the number of female scientists in a country or in a discipline. And when MFR is higher than 1, the number of men is bigger than the number of women. And when the MFR is lower than 1, it reflects a greater number of women in a discipline or country or any other unit discussed. And you can see here on the right how MFR looks by discipline. You see enormous differences in physics and computing and mathematics, big but still much smaller differences in business and humanities, in biochemistry. And if you look at the medicine, and also if you look at the figure here, you see that women on the right and male scientists on the left, that women are predominantly in a couple of disciplines. It's a snapshot, just 1 year. Let me stress again. It's medical sciences and it's biochemistry and a bit of other disciplines. And we look at countries again where women are concentrated. Again, it's the US, it's Germany, UK, France, Italy. These are the places where the number of female scientists, publishing female scientists, or research active female scientists in 1 year is bigger. And if you look at this MFR ratio, you see there's only a couple of countries on the right in this table in which the share of male and female scientists is more or less similar. And these are 3 countries in Southern Europe. It's Spain, Italy, Portugal. Is a couple of post-communist countries, Slovenia, Poland, Estonia, Latvia, and it's a single Scandinavian country, Finland. There's only 1 country in which the number of publishing men and women is equal. And interestingly, it's Italy. Almost half of all female scientists globally today publish in medical sciences, and 3/4 of females are located in just 5 countries. You have the names here: it's US, UK, Italy, Germany, and France. There's huge concentration of publishing female scientists. And now, not a snapshot view, but a longitudinal view of the global scientific workforce. So 3 decades. Well, the picture needs several elements. The number of scientists at the starting point, 1990, the number of scientists at the point of arrival, 2020, and the percentage change. You see the changes here. Medical sciences and biochemistry and engineering use a different scale. They are big. We are talking about, say, almost 1 million scientists today. So you have different scales, but wherever you look, the slope is different. In this figure, slope goes down. The highest is for physics and sociology, like most aging disciplines, and the slope goes down and down and down, but it's always positive. So the academic workforce is aging. Now, numbers and disciplines. Some disciplines are expanding faster, and others are expanding slowly. You see what is expanding fast. It's computing, it's business, it's humanities, interestingly, and it's sociology. And you see the change on the right in this blue square, the change within the 3 decades shown in percent. Overall, we are expanding. I know we have to use all those limitations. We are talking about a global database. We are talking about only publishing scientists, but still there are more and more and more of us. In nominal terms, however, it's medical research that rules. You see the change almost 700,000 more scientists compared with biochemistry and all other areas and disciplines in which these changes are small. You see the changes here. Medical sciences, more than 600,000 new unique scientists. And then look at humanities or business or mathematics, which is not surprising perhaps, and economics. The increases over the 3 years are very small. It's just a couple of dozens, between 20 and 30,000 new scientists. So medical sciences rule globally. In medical sciences, there are more new scientists than in the ranks 2 to 6 on the right shadowed, and more in all other remaining disciplines, ranks 7 to 26. So absolutely, the action is in medical sciences, understood, let me explain it, as medical sciences related journals and medical sciences publishing scientists. Now, very briefly, the power of medical sciences and what happens if we remove it from the picture. On the left, when medical sciences are included, you see that the changes are small compared to medicine. If we remove medical sciences, we see that biochemistry is a big area, and then we have some increases in the number of scientists in other disciplines. But still, when you look down, you see that in many disciplines, the increases are small. So we have big increases in say, biochemistry or engineering or even sociology, but very small in humanities, business, mathematics, economics, etc. We see the difference, especially important perhaps in the US case, but also in Europe, the differences between social sciences and the humanities. Expansion of social sciences in the period, and not so much expansion, but still not contraction in the humanities. Let me explain. When I was starting this research, I had a fantastic theoretical framework in which I had classes of expanding and contracting disciplines, but none of the discipline is finally actually contracting. And I had also disciplines which were aging and which were graying, so to speak, and which were rejuvenating. But actually, none of the discipline, finally, the median age is decreasing over time. So I had to accommodate the framework to the reality, which is presented here. Well, again, scientists in these 3 decades by country, 3/4 of scientists in this period came just from 6 countries, and you see these countries on the right. The absolute majority came from the US, but it's more than perhaps we would expect. There are also only 10 countries with less than 10,000 scientists, which are not here in this picture. And interestingly, there are newcomers. I'm especially interested in those newcomers to the global picture. And Poland, my country, is such a newcomer. Just to give you an example of what I mean. In the past 30 years, there were 76 individual Polish scientists. But in the past year, just 1 year, 2020, there were as many as 51,000. You see the expansion of some countries. And Poland here is rated as 13th, even though in terms of publications, it's rated about 17th or 19th in Scopus. So you see there are many people who don't study too much, who don't publish too much. There's expansion in terms of people, but not expansion in terms of publications. And it's interesting to see the differences. A lot of people, but not so many papers. And we can see papers through Scopus or Web of Science, but we can't see people there. Well, perhaps finally, well, we studied scientists by age group, gender and discipline, just 1 year, and then let's say 1 year. You see the pyramid is pretty typical. Interestingly, in all disciplines, at least half of publishing scientists are young. And by young, I mean those with 10 years academic age or less. You see, so the structure is more or less good. because the majority of scientists are young, and there are no differences. Even in physics or in mathematics, which tend to be older, there are more than 50% of young scientists. And I zoomed here on young scientists, and I zoomed here on old scientists. Let's have a look at young scientists. And perhaps this is one of those points which were surprising and potentially most interesting. 1 year, all disciplines and gender. You see women scientists on the right and men scientists on the left. And absolutely surprisingly to me, in every single area, the share of young scientists, the share of young women scientists was higher than the share of young men scientists. This is really surprising. I knew there would be a lot of young people around because we can see it and we can see it through the data, but I never realized there would be so many female scientists around, more in every single discipline. It's both in the humanities. You can see, let's focus on the humanities for a second. Those aged 6 to 10, you see almost 30% of women and 24% of men. And if we focus on 5 and less, so very young scientists, it's 8% for women and 7% of men. And it's humanities. But certainly if we look at physics or mathematics, usually very old or viewed as very old disciplines, it's the same. It's exactly the same. More women everywhere. And it's interesting to remember, we know from productivity studies that there are more publications by men, and it's true. But from this demographic research, we know there are many, or at least more women scientists around, but they are not so much productive. So there's huge, I would say, untapped potential of women in science in every disciplines. They are present, they publish, but they are not as productive for many reasons, also institutional and other. We have studied it for years. Now, all scientists is not surprising. Male scientists are dominating the oldest cohorts. You see, let's focus for a second on biochemistry and genetics, called bio here. You see at those 30, 35 or 40, 40, 41, 45, those old scientists, men dominate. It's not surprising actually, because we know men have been in science for decades and women have not been for so many decades. So if we look at 46 plus 30, that would be age of about 70 and more, or even 75 or more. We see the domination, but no matter what, we also see differences between, so to speak, younger disciplines, like computing, with a relatively small person on the right, with relatively small percentages of old people, and say physics, I would say an older discipline with a lot of people, and especially a lot of men in really older age. 31 to 35 is like 60 to 65 in terms of career age. If you add 30, more or less in the OECD area, if you add 30, it's like career age, or I would say even biological age. So final words, just 2 slides with some implications. We know that globalization science is ongoing, but also new data sets emerge. We can seize new opportunities. We can examine scientists globally. It was absolutely not possible, say 5 or 10 years ago, in terms of age or in terms of gender. It was absolutely impossible. So new data and new methodologies, I would say, pay off. They pay off. And new large-scale global pictures are possible. My picture is one of them. There may be many of them, but possibly the zooming in on old and zooming in on young people, young scientists across disciplines globally, is potentially pretty interesting. I would say that age by itself is important. It used to be just a part of productivity studies. Now it's becoming important because the data are available. But certainly the data are commercial, the data are structured, the data are raw, they cost a lot, or you need collaboration with big companies, but they are useful. If you want to know age profile and gender profile in science, my answer is we have to use commercial big data because there's no other data around at the moment at the global level. So I'm suggesting a move from the publication to the scientist as a unit of analysis and as a unit of analysis, which is I would say, a new approach. We know all the limitations because bibliometric data has been criticized for decades. So we know all the limitations and no criticisms. It's good to know it. Finally, all disciplines are slowly aging. The speed of aging varies, especially zooming on different subsamples matters. For instance, we can select disciplines, or we can select young or old scientists. Finally, it's a nice finding. There are more young women than young men scientists across all disciplines. I would say it's a revolutionary change if we look beyond these years, if we look in the future, because implications are powerful. So if you compare productivity studies and demographic studies, we see that there's untapped potential of female scientists because of women's productivity is lower, but there are more of them if you look at young scientists. Well, concentration, the final word, the final sentence, concentration. Medical research dominates. 40% of all scientists globally are in medical sciences. Almost half of women scientists are in medical sciences. 3/4 of women are concentrated in 7 countries. That's also an important finding, just 7 countries. 3/4 of scientists are concentrated in 6 countries. And we don't mean, or I don't mean here higher education academics, I mean publishing scientists, which is a different story. Well, when new jobs emerge, they emerge just in 6 disciplines. Just in 6 disciplines, and in those disciplines, numbers are big. So I'm suggesting that the global dimension, which I've been studying in this presentation, the global dimension of the science workforce, is important. I can't say it's as important as traditional cross-national dimension in which we have Americans and Germans and Australians, etc. But it tells us something. We know about concentration, we know about women globally, we know about young women and young scientists globally. And I would say it's a new view because of its approach is somehow new, because the data are new, data sets are new. So thank you so much. It's probably exactly 40 minutes as I promised. I'll be happy to discuss it further with the discussant and with you. Thanks so much. I'm stopping sharing the screen right now.
Thank you, Marek, for this fascinating presentation. And I already saw comments and questions from the audience. Mark, Arlette, Christina, Özgur. But first, I would like to prioritize to give the word to Samin, since he's the discussant, he's a real expert of the data collection. So it's up to you, and then we come back. There will be room for everybody to comment and to ask questions.
Thanks a lot. Thank you, Marek, for the presentation. So I don't want to keep everyone's waiting, because I see that there are quite a few hands raised and many questions. So I just want to keep my discussion very brief. So I pretty much agree with many of the points that Marek raised about the potential of bibliometric data, the fact that it has such a great level of granularity that we can do many different dimensions of analysis, and also the change of focus from publications as a unit of analysis to individuals as another unit of analysis, which is more, I think for many different purposes could be more easily understood and would be more relevant. So while I agree with many of the points that Marek raised, I think the limitations of bibliometric data are not just important, but essential for us to know. So Marek said that we should know these criticisms. I would say it's absolutely essential that we would know them, and it's important that we also do something about them. So I noticed that the process for the analysis, started with a step one, measuring the age, step two, identifying the most likely gender for the authors, and so on. So the way I think about analyzing bibliometric data, all those steps of measuring something or plotting something, taking median, and so on. I think these are all the last steps of the analysis, and the way I usually approach these sort of projects is having several steps of doing, sanity checks about the data, checking the data quality issues and how they possibly affect the results. So, as many of you know, one important challenge with using Scopus bibliometric data for studying individuals is the limitation of Scopus author ID. So Scopus author ID, comparatively, it offers a decent level of precision and completeness. As far as I know, something around 98% precision and something around 90% completeness. But for many of the analysis that we do on individuals using bibliometric data, that 2% lack of precision actually means something. And I think it's important that we have an automatic way of dealing with data quality issues, dealing with records in the bibliometric data set that are more likely to have suffered from that lack of precision. So I know that this work is an ongoing work, and there are still many areas for improving the analysis. But I think those data quality checks are really important and should be done before starting the analysis. So another point I want to make is about the general idea of big data, big bias. So whenever we talk about big data, we are excited that it has many features. There's no data collection involved. We just access the data. Of course, when it is commercial, there are some other challenges. But typically, when we hear big data, we are excited about it. But we also need to consider that with big data, we can have big bias, especially when there are these hidden algorithms that are giving the structure to the data. There could be one simple issue with how the algorithm structures the data, and that could reduce the reliability of the insights that we would get. For example, I noticed in my own work that for some of these Scopus publications, especially those from 90s, sometimes there are publications for which all the affiliations are linked to all the authors. And then when we check the publication, we see that that's incorrect. So this must be from certain publication venues where this link was not there, but somehow this simplification was made. And so I would say we need to also be more cautious when using bibliometric data and generally digital trace data, but that's how we can hopefully benefit from the advantages that it offers. So I don't want to keep everyone's waiting, so maybe we can move on to the Q&A. And I also have a couple of questions of my own that I would like to only ask in order, hopefully after a couple of other people who have hands raised and questions in the chat.
Thank you, Samin. And I suggest we go straight to accumulate some questions. This will help us manage the space. So I see Mark, who is waiting since a long time.
Yeah, dear Benedetto, thank you. Dear Marek, yeah, thank you very much for your presentation. The first time I see your work presented, and I'm really happy, and it's really fruitful. But I have some questions or remarks. First of all, you have selected some people, and I do not really understand what effect that will have. And I would love you to look at it, what the difference makes if you put these people back into your sample. The people I mean, or the publishing academics I mean, are those who are affiliated to countries and or to two disciplines. Because I know, at least for the German system, that there are a huge number of people that have switched countries and worked in Germany and then in the US. As my doctoral father said, in Germany, it's very important to beam to America. The BTA is a very important step to go back in the academic career. That is one question, and that makes maybe a lot of differences in your analysis. Another point is that I wonder what you say about changing publishing behavior in the course of these 30 years, because we see much more multi-authored papers than before. So I wonder if that effect makes this aging a point, because more senior authors are included in a paper because it opens the door a little bit more. And that this is one area that is important or may be a factor. Another thing is, I wonder if you can control for including new metadata. I know from the humanities and social sciences that the metadata availability in the databases is rather poor, for example, the 90s. And some of your findings may be based on better availability in these areas that are coming back in recent years. And so I'm also would love you to look at the dropouts. So who is going, I mean, you show the age pyramid, and I would love you to do some who is dropping out over time. So which account is maybe inactive for 2 or 3 years and not coming back? So these are the points.
And then I would collect a couple of additional questions. Arlette is also waiting since.
Hello, yeah, thank you so much for this inspiring presentation. It resonates really well with me because I was thinking for some time to use author data for studies of scientific capabilities. And so I'm really interested in your work. I have 2 questions. One is methodological. I did not understand how you sample the scientific workforce for 1 year. I understood how you sampled the 5 million scientists, basically, but how you derive 1 year slices. Could you explain that, please, further? And then my second question would be, can you say which countries invest in the expansion of medical research? I think that would be interesting to know.
Okay, Benedetto, can I start?
Yes, I would just take the question of Bayozgur and then give you back the word so that we make a first round.
Hi, I hope you can see me. Thank you very much for this great presentation. It's very impressive. I just wondered that, have you normalized the academic age with the age of countries? Because I thought that some of the aging in academy is due to the aging in society in total. So we can compare the aging in academies across countries. Thanks.
Okay, Marek, for you for a first round of answers.
Okay, for a first round. It looks like you would like me to do everything. I mean, absolutely everything. And it is absolutely impossible. So I will answer some questions and give some suggestions. Well, methodologically, how we followed, for instance, how to define a person as a sociologist. Yeah, there are many ways. But what we did, we took all papers of everyone, lifetime, articles only, And then we took all cited references in those papers, lifetime. And then we put it all together and we found the mode. And if the mode is sociology by sociological journals in Scopus, the person is defined a sociologist. Obviously, it's a proxy. It's a big approximation, but we use approximations in all this presentation and all this research. Otherwise, we wouldn't be able to say a word. So I would say this is a big approximation. And now we could be working on any of these questions for a year, any question, comparing, thinking about any detailed issue. Perhaps it's worth it, but it's not for everyone. I would say a big picture is useful. It can be criticized for a long time and it's fantastic, but still we want to move on showing the, well, options that big data, commercial big data can open. Because I've been studying academic age and biological age for a long time. I did a study on Poland, a pretty detailed study, and I know how academic age was used. So I'm just showing that there is a potential at the global level. I'm not saying it's interesting or not interesting, but I'm using it. There are many biases, like Scopus has its own biases. Also, the question who counts as a scientist in this research. We said, okay, we count as a scientist a person who has a couple of attributes. One, at least 3 publications. Yeah, so it's not an occasional writer, but you know, well, a standard writer, 3 publications. Then 3 publications, at least 1 publications in the past decade, 2010, 2020. So pretty recently, and 1 more 3 publications, but not in a single year. There's a number of conditions you have to meet to enter the sample. And looking at our letter about the sample for 2020, who these scientists are. These are all scientists who publish in this single year. So all other conditions don't count in this case. Everyone who published in those 38 countries in this single year in all journals in the form of article. And when I'm thinking about this normalization to the aging of society, certainly we in academia age as our societies age. But basically major or the largest OECD countries are aging at a similar pace. We are not talking about India or about China or about Africa. We are talking about advanced economies. So it's good to normalize it, and someone can do it. But it's almost impossible to take all those various roads at the same time in a single research, which wants maybe to show something, maybe something new, maybe something interesting. Probably this approach to age is innovative. The question about disciplines is very valid. And STEM disciplines are well represented in Scopus. Non-STEM disciplines are not so well represented in Scopus. But still, if you look 30 years ago and 20 years ago and today, it was not well represented and it's still not well represented. So you see the pattern. I could easily cut all the disciplines to 14 STEM disciplines: science, technology, engineering, mathematics, and medicine. Good. But would it be more interesting to cut all social sciences and humanities and economics, etc.? They have always been underrepresented and not much is changing. Well, we can normalize for the changes. We can normalize for everything. But I would say it doesn't always pay off if you brush a pretty big picture, as I'm doing here. It's a pretty big picture. I could discuss every single methodological issue. For instance, gender. Okay, we used only those scientists who had gender in OECD countries. And certainly Scopus had its own 0.85 threshold to allocate gender. We had a lot of millions of nulls, which is no gender specified, and we cut it from the discussion. Certainly, as Samin said, every step should be quantified and error should be, well, quantified. It's true, but at the same, it's a big approximation anyway. So, well, that would be more or less the answer. There are too many questions maybe to remember for me, but probably I didn't answer all, or maybe most, but yes.
So thank you, Marek. I would have a couple of additional questions which go into the same direction, but maybe with a different a bit of a suggestion. So when you presented, and the presentation is indeed great, I wondered what you are observing and what could be the source of bias. Some have been discussed, but of course, one question when I observe the growth, one question is whether I am just observing the growth of the increase of the coverage of Scopus over time. We know it increased a lot. Or whether it was already mentioned, we are observing changes in the publication practices. So more people going to Scopus journals, PhD students being more involved or less. And my feeling is these biases are unavoidable, but I have a feeling some are more relevant for some aspects of the analysis. And one would wish, I'm speaking as a reviewer, I would wish a counterfactual. So for example, if you look to growth over time, I would expect a counterfactual keeping the Scopus journal perimeter constant over time, for example, or this kind of things. So I would encourage really everybody, because we are all discussing about these sources, to take with their limitation, but to try to find counterfactuals or evidence that it does not bias the analysis on some dimensions, but it may be on other dimensions, I do think. My second question is whether you try to model the aging process, because when I think of the aging process, it's a balance between stock entry and exit. Now, you could imagine, for example, the aging process is mostly due to the fact that there has been a wave of entries at some point, and then a number of new entrants decreased, and then you had an aging. Or it could be that the exit diminished over time, or simply that careers have become longer. I know that this cannot be easily modeled, but maybe developing some attempts to describe these dynamics mathematically and to make a test to fit the data might be useful. That's my second comment.
Yeah. Let me answer as long as I remember the questions, please. We did a sub-study about attrition, so who comes to disciplines and who disappears by countries and by disciplines, because we have stock, which is who is around, and we have flows, like people coming into discipline and going out of discipline or exiting. We did a lot of work on this, but I didn't put additional slide here because it was still too much. But it's one of the most fundamental issues. Who is coming out of science? And I would say it's a lot of women coming out of science. We had a threshold, like working for 3 years in a row, and then maybe adding two more years, and then if there's no more publications for some time, this person is lost from the study. We spend a lot of time, but it's not yet direct. But you are right. If you look at statistics traditionally, it's just numbers. If you look at unique scientists, you have IDs, so you see who comes and stays, or who comes and disappears for 3 years or disappears forever. It's enormously interesting dimension, but it's we did some studies and manipulations, but I didn't present it. And coming to back to the first question about biases, some of them are enormously important and some of them are less important. For instance, I would say this gender dimension is enormously important. That's why we stay to the OECD. There are many people around in bibliometrics who do global studies with all countries. But if you look at China, or in some countries, the coverage of the definition of defining of women doesn't exceed 30%. So we have nulls and nulls and nulls around. You just don't know the gender. So one answer would be keeping to OECD, gender. If you look at disciplines, certainly it's a great proxy. You took all references from all your papers, from all your life, and you say, Marek is a sociologist. Maybe he is not, who knows? Big approximation is using ACLS system of disciplines from Scopus. I'm not talking about disciplines. I'm talking about Scopus defined disciplines as used in their journals. There are many approximations, and certainly there should be counterfactuals, like comparing what would happen if, or taking one country for comparison. We took Poland for academic age, and the correlation between academic age for Poland for STEM disciplines and for Poland biological age, which we had from National Registry, was like 90%. So correlation is pretty high. There's a number of counterfactuals like this, and single nation studies which could corroborate some approximations as valid. But obviously it's almost impossible to do it at large scale. We can do it for some countries, for some dimensions. Coverage is another issue. We know that coverage is increasing. There are more and more journals. We know the numbers change from year to year. So some countries are more present. But if you look at Anglo-Saxon countries and at STEM, I would say that journals have always been there, and they are there. And again, for some countries, for some disciplines, it works. Overall, we know that the expansion is in terms of journals. And also you mentioned collaboration, but I'm referring not to publications, but to people. So individual IDs, individual people, another approximation. I'm not talking about people. We are talking about authors' IDs, not real people. It's again, approximation. I would say, to finalize, there are approximations around, and it's good to discuss some of them, and we will do this, but it's almost impossible to measure the multiplied proxy, or to measure the multiplied error, because errors certainly multiply if you don't take so many women, or if you finally don't take so many countries, or your disciplines are coming from a different register, Scopus, and not, well, American classification of disciplines. Your errors may multiply. And I would suggest for myself, make it clear and discuss it, but don't try to normalize this type of research to every possible error and every possible approximation, because probably it's impossible. Probably, if you think of surveys, it's also total survey error. It's a bit easier. You have error here, error here, and you have total error survey. In this case, we would need something like total error for big data. Probably nobody did it, but certainly it's enormously important. Enormously important.
Thank you, Marek. I want to say my attitude is like when I'm checking statistical work. There is no way of checking for all problem biases or problems or missed errors, but there should be some confidence that the multiplication of small errors does not change dramatically.
Yes, definitely.
And we should not just stay in the fact that we have millions of observations that this put us in a secure place. But I would like to make a second round of questions or comments. First, I see our discussant. So Samin, it's to you the word.
Thanks a lot. Yeah, so I have a question about the population pyramids, and I was wondering how, if you have considered something like a survival, that, you know, if people do not publish for a certain number of years, you remove them from the sample at some point for the purposes of producing those population pyramids. So that's my first question. And my second question is, you know, pretty much how I was thinking about what you were analyzing as this expansion, as you would call it. I was wondering, with the current analysis that you did, if we consider that the ground truth, I'm just playing the devil's advocate, if the ground truth is that the science has not expanded, it has actually shrunken, with the current analysis and the fact that Scopus coverage is increasing, and also over the past 30 years, perhaps the publishing culture has also increased in terms of frequency, will we be able to see that contraction? So these are my questions. Thanks a lot.
Yes.
Okay,
Yeah.
so Marek, I would like to collect with you
Okay.
time
Okay, absolutely.
questions. I see Charlie was a question.
Mute, sorry. Hey, Marek, thanks for your presentation. I'm just curious, you mentioned something about how you took a 3-year slice earlier because that worked slightly better at the moment. I'm actually sort of fits with Samin's question, struggling with attempting a survival analysis where we actually do use PhD years since we have all this data for academic age. And we're having complicated internal discussions on what a better time frame would be, which of course is partly dependent on how big the time is that I actually have data on, which is not as extensive as you do. But partly also because some of the tools you might use sort of overestimate the effects of zeros, of years without output. And that kind of links to the question on when do you choose to censor? So I'm really unclear on to decide what to do at the end of my sample. Because if I understood you, you say, well, you need to have a couple of papers. They cannot all be in the same year. It needs to be spread on a sort of time frame. But I don't have data post the end of my data set. So at some point, I have to decide then this is the last cohort. And have you any fantastic solutions?
So Marek.
Okay. Yeah. First, I mean, I forgot the question actually.
The first one was population pyramids and
Okay. Thank you. Yeah, we use the following approach. If someone does not publish, if someone publish in a year and then does not publish for the next 3 years, it's removed from the population. And that's why the attrition in our samples are huge. If we took everyone who published once, we would have had 33 million people. But when you used all those thresholds on all those limitations, we arrived at fairly 5 million. I felt it as a loss, as a personal loss. But at the same time, I wanted everyone to have clear gender, yes or no, male or female. In this case, it comes from registries, it's just male or female. And I wanted one affiliation. This is another approximation. We removed all scientists who had multiple affiliations in terms of countries. So one country, okay, 2 different institutions, but we just removed from analysis because we knew we are not able to capture those 10% of traveling scientists, which you analyze so deeply based on global data. There's a couple of, say, 10% of big movers or movers around. We had to remove those scientists. There's a lot of those type of methodological decisions, and thinking about Charlie, what to do about this attrition, whether it should be 2 years or 3 years or whatever. We had data for 30 years, and we were looking at those millions and whatever happened. For instance, we had in this part, which I didn't advertise today, which is incoming and outgoing, those pictures with incoming and outgoing over time. We had those who, and we had also returning. So we had some scientists who were publishing for a couple of years, then they stopped for 2 years and they were like leaving. But if they returned 3 years later or later at any point, we call them returning. So we had incoming, returning, and generally staying. And quite a lot of people were staying for 1 or 2 decades. But if you thought of 3 decades, I remember it was just 100,000 people. Just 100,000 people out of 5 million were publishing anytime, not every year, as in Ioannidis and Clavans every year, but from time to time for 3 decades. So we are not as stable in academia as we thought. There are so many people staying for 2 decades. Not so much. It's 100,000 3 decades, maybe 200,000 2 decades. And these data are obviously interesting, but it's not enough to say it's interesting. I didn't show it because there are too many stuff like this. But yes, we had to answer these questions. So incoming, outgoing, and returning. We use the category of returning.
Thank you.
Okay, thank you. There is still an opportunity to ask more questions if you are not exhausted by this tense discussion. I feel Samin.
Yeah, thanks a lot, Marek, for your answers. I have another question. So this is something that it was kind of challenging also for our project. So when the start year of the data that we have access to is 1990, I think it is, quite tempting to also start, reporting all of the measurements or most of the measurements starting from 1990. But later on, we kind of had the, impression that there's also some benefit in the year of first measurement to be different from the year of from the first year of the data set. So something like, starting from 1990, but maybe for the first 10 years, we don't measure anything, but we just, let these people, come to the population, and, based on those filters, we keep them or we remove them and so on. But then the reports that we want to have for the analysis of the cohorts or the temporal dimension, maybe starting from 2000 or something like that. So what do you think about this approach?
Yeah, it's a fantastic suggestion. Actually, in many places in this presentation, instinctively, I use, remember, cross-sectional 2020, over time longitudinal 2020, instinctively 20 years. It's natural. We know about the data coverage and everything, about Scopus, etc. So probably it's useful to consider this, having the data from 3 decades. Actually, we have the data from many decades, because when I'm seeking this academic age, it's from publications from the 80s or 70s or whatever, because the data are there. It's not available to us, but raw data in Scopus lab indicate all those first publications for 70 years or 60 years. We put a stop. Scientists cannot be older than 80. Okay, it's 30 plus 50 maximum in general for patterns. So yes, I like this idea of maybe reformulating the 3 decades story to 2 decade story. Then looking at Benedetto, the coverage issues would be a bit smaller. There will be many more journals around already indexed. It's nice to have less criticism. So it's quite a good idea to have full data or fuller data, but use only say 2 decades. We know that the trend would be the same. It's aging. Maybe the differences will be smaller, expressed in years from within these 2 decades, but the story will not suffer. So thanks. I mean, we will definitely consider it.
Thank you. There is a further question by Radim Ladik. Yes.
Yes. Hi, Marek. Thank you for the presentation. Some of my questions were already answered, but one thing I would ask you about is, what does it really mean when you say the scientific workforce is becoming older? And what I mean, of course, like if the median age is increasing, I will probably encounter, more people of certain age, I don't know, at a conference or something. But when you show the result for engineering, for example, as the sort of the least aging discipline, it left me wondering if in this concept of academic age, what is it you really capturing? Because what does it mean to die academically? You stop publishing. And I imagine in engineering, you have lots of people who exit the field because they get industry jobs. And so it's just like the young postdocs taking up their places, and that keeps the discipline younger. So what is really the mechanism at play there? Maybe might work differently, different disciplines. Maybe what you're capturing is not getting older, but the disciplines that have older workforce are disciplines with more job security, stability, more stable careers in the academia, perhaps. Thank you.
We've been struggling with these definition issues for quite a long time. What would it mean to have a graying discipline or a rejuvenating discipline? We have no rejuvenating, as we see, we have all of them are graying. So I was thinking it's a combination of median age. The median age is a simple story, but it doesn't suffice. You need also these pyramids and compare a pyramid to say 20, looking at Samin 20 years ago, and the pyramid today. And if this pyramid, those shares of old people today are higher, those after 60, 70, well, we express it certainly in academic age, but it's like biological age, so we know what it means. We just add about 30 and we have biological age. So if this pyramid is thicker in the top, more higher percentages of those old, I would say it's graying. It's getting old for a discipline, and different disciplines can have different pyramids 20 years ago and today. You are right that the medium age is not saying everything. So I'm trying to combine the median age moving up with this pyramid approach in which there are more and more old people. It was not in this picture today, in these figures. I was showing you only 2020 pyramids, but the idea is to compare pyramid 20 years ago and today, not in numbers, not this expansion through numbers, just academic age, and see that really those age 60, 65, 70 biological age, which is just approximation, is bigger. These pyramids are thicker when you look at the top of them today and at the top of them 20 years. Still, it's just some approximation again.
Thank you. But I think the pertinent question for me is still, what is the mechanism behind? And of course, you could think of different mechanisms, one of which being also that people continue publishing on Scopus journals after a certain age. Maybe in the past was not the case. So I mean, what I really would advise is to try to model a little bit the process. I will allow a last question. If there is still one. So otherwise, my feeling, we are really in something. There are incredible opportunities, and as when every time you have incredible opportunities, you have methodological questions arising and convincing other communities that these data indeed provide robust results, and pushing from the data towards interpretation. So I thank really Marek for your presentation and some
thank you so much.
Helpful comments, and all the audience for questions. Now, this was the last RISIS Research Seminar for this year. The series will start again in September, and we are welcoming proposals of presentations dealing with science, technology, and innovation and higher education.